Good morning students. Today we are going to discuss few important topics from chapter 5, that is magnetism and matter. It is continuation of our previous discussion. Now the first topic which we are going to discuss is the properties of magnetic field lines. I think most of you know the properties, though we are repeating few properties here. Number one is your magnetic field lines are continuous and closed curves traveling from North Pole to South Pole outside the magnet. And inside the bar magnet it is just the opposite. It travels from south to north. So this is very common property, I think most of you know. And number two, the tangent at any point on the magnetic field line gives the direction of magnetic field. So if you want to find the direction of magnetic field at any point, what you have to do, you have to draw tangent at that specific point of the field line. Now third point is your two field lines do not intersect each other. If they intersect, what will happen? You will get two field direction which is not possible at that specific point. So these properties are very simple, I think most of you know. Now next topic which we are going to discuss is your bar magnet as equivalent current carrying solenoid. So here you do have a solenoid of length twice L, and we have considered two axes. One is your x-axis and the y-axis, and O is the origin, and it is nothing but the midpoint of the solenoid. Now left side is your L, right side also your L, so it covers 2L. Now P is a point where you have to define the magnetic field. Now what we'll do here, we'll consider a segment of that solenoid of length dx, and with that segment we will try to find the magnetic field at P. Now I is the current flowing through each turn, so dx element contains many turns. So if we consider n is the number of turns per unit length, then the total turns will be your n dx, is not it? And for n dx we have to define magnetic field at P. Now already we have discussed field due to a current carrying loop, and solenoid is nothing but a combination of the loop. So basically we will try to find the magnetic field at P due to the dx, and dx contains many turns. So if n is the number of turns per unit length, then the total turns will be n dx. So you see this expression already we have defined for a single loop. Cos theta equal to sine of 90 minus theta, and it is your perpendicular by hypotenuse a by r equal to a by root over a square plus x square. Now you do have a current carrying loop, and I is the current, so dB is the magnetic field, and it is perpendicular to r as per your Bart's law. It has two components, one is your dB cos theta and the other one is dB sin theta. If theta is the angle made by dB with x-axis, so if theta is the angle made by dB with x-axis, then 90 minus theta is the angle made by r with x. So it's a very simple geometry. So for every element you do have a corresponding diametrically opposite element for which the magnetic field is there, and for that the component dB sin theta cancel out and dB cos theta gets added up. So ultimately if you want to find the magnetic field at the point, a specific point at a distance x, what you have to do, you have to sum up all the dB cos theta for each of the element. So ultimately magnetic field is your summation of dB cos theta, and dB is nothing but is your Bart's law mu naught by 4 pi I dl sin pi by 2 by r square. R square is nothing but is your a square plus x square. So dl is nothing but is your 2 pi a, that is your circumference. So ultimately if you substitute the value of cos theta, the final expression will be mu naught I 2 pi a square 4 pi a square plus square 3 by 2. If you consider n dx turns, what you have to do, you have to simply multiply. Now x is the distance from the center of the loop to the specific point, is not it? Now P is a point and r is the distance from the center O, and we have to define the distance of the point P from dx, and for that what you have to do, you have to subtract that x value. R minus x is nothing but the distance of that segment dx from the point P. So whatever we have got here in place of x, what we have to do, we have to replace r minus x whole square. I think you have understood this part. Just you try to compare. It's a very simple. Now to get the magnetic field at point P due to the whole length of the solenoid, what you have to do, you have to integrate by considering dx as your variable, because it spreads throughout the length of the solenoid within the limit minus L to plus L. So if you integrate, it becomes L plus L, so it's your 2L. Now magnetic moment, if n is the number of turns per unit length, then the solenoid contains n2l, that is your total turns, and I is the current in each turn. So n2li gives you the current for whole length of the solenoid, and area of each turn is your pi a square if a is the radius. So m is the magnetic moment, so you can express this expression b equal to mu naught by 4 pi 2m by a square plus r minus x whole square 3 by 2. If r is very greater than a, obviously r is very greater than a, and if r is very greater than x, then you can approximate this one, mu naught by 4 pi 2m, that's your r cube, and which is same as that of bar magnet. So you can say that a solenoid, a magnetic field due to a solenoid, is same as that of the magnetic field due to a bar magnet. That's why we have written bar magnet as equivalent current carrying solenoid. So for this topic, what you have to do, you have to compare your previous class. So this is very important. You have to continue your study. If you don't understand this topic, that's the magnetic field due to current loop, then definitely it's not possible for you to understand this topic, because it's interrelated. Now next topic which we are going to discuss is your bar magnet in a uniform magnetic field. So bar magnet we have placed with its axis at an angle theta with the magnetic field, and the field is uniform. Now it has two poles, north pole and south pole, and here we are considering q is not charge, rather q is the pole strength. So force will be qb vector on north and qb vector on south, both are in opposite direction. So what we have done, we have drawn a perpendicular to the line of action of the force. So if you have to define torque, force, perpendicular distance between the line of action of two forces. So force is your qb magnitude and the perpendicular distance nm, so it's your qb 2l sin theta. It's a simple nm perpendicular. If you find sin theta perpendicular by hypotenuse, so 2l sin theta. So m is your magnetic dipole moment, that is your m equal to q 2l. Q is your pole strength, so it's coming out mb sin theta, and in vector notation tau vector equal to m vector cross b vector. So this is all about. Please go through this topic and try to find out your doubts. Make your habit to ask questions during the class, and definitely you have to relate this one, loop, magnetic field due to a loop, to define magnetic field due to a solenoid. And this expression you are not supposed to derive for the bar magnet, magnetic field due to bar magnet. This is out of syllabus, so we are using directly this expression, b equal to mu naught by 4 pi 2m by r cube. M is nothing but is a magnetic moment. So this is all about. Please go through and make your notes. Answer very simple, and mathematics is there, just to try to understand. And if you have any doubt, please ask. Thank you.